So indeed, I'm not Richard Cushman. Okay. So no, he wrote to me, and then well, he's been retired for quite a while. So he asked me if I could take it off his talk, and anyway, he sent me his paper, and well, I checked with him, and you see what he's done. What he's done is part of a bigger program. So I thought that since this is a multidisciplinary audience, so I thought it was better to probably to tell you the general story, and then at the end I will tell you exactly the particular example that he worked out for the paper that he submitted to the conference. So what I will do is exactly that. So I will tell you the general theory, even though looking at the faces that I see in front of me, many of you already know it. But nevertheless, I've seen that in this community you are quite fond of the historical remarks and putting things in context and so on, something which, as I grow older, I also appreciate very much. And anyway, I hope that with this twist, Richard's result will be better put in context and appreciated. So let me start with this general theory. And the general theory is actually this. And so, well, this is the American or the English version of the well-known famous book by Jean-Marie Souriau, the first edition in 1968 by Duno, I think it was published. And actually, you see, it's translated by C.H. Cushman de Vries. So this is actually the late wife of Richard, who, even though she was Dutch, she happened to speak very well French. So she's actually the one who took care of translating the book into English under the supervision of Richard and Guy Steinman. And by the way, Guy Steinman, he's a professor in Lille, so he could have translated it himself. But anyway, so she's the one who took care of doing it very carefully. She dedicated a lot of time. She was a wonderful lady. So I had a chance to meet her. And around the dates in which she took care of this translation. But in any case, the theory that I'm going to tell you about is in this book, which contains many other things apart from what you will see in my talk. And the setup is extremely general. So let me in 3 slides tell you what the setup is and what Richard did in his paper, in the particular case of the affine symplectic group, okay? So anyway, the setup is something that we saw already. So we are going to be in a Poisson manifold. We're going to be using the Lie Poisson structure that we saw in Professor Saboron's talk. And then what we will have is either a group action that respects this Poisson structure or a Lie algebra action. Because actually this will be going around the momentum map and its equivariance properties and its Poisson map properties. And as you will see, there is this very nice connection between being Poisson and being equivariant, or respecting the Lie group or Lie algebra structures. So in the Lie group case, we will have something like this. And then we will say that when we have a Lie algebra structure, we will say that the action is canonical when we respect the Poisson tensor. And then there is this proposition in the Lieberman-Marl's book that, well, basically, if you have this, you have it too. Anyway, and then, so we need the momentum map, which is the other ingredient in this talk. So I'm sorry for the experts in the audience, but you see, this is a central object in geometric mechanics and in symplectic and Poisson actions. So just in 2 words, so the momentum map, you define it as a map between the symplectic or Poisson manifold you are working on into the dual of the Lie algebra that you are using, that is the subject of this Lie algebra or this group action that respects the Poisson structure that we were talking about. So first observation, in order to define it, you only need a Lie algebra action. So here, if you see, there are no groups in here. And then you say that you have a momentum map whenever actually the infinitesimal generators happen to be Hamiltonian. And then, well, basically taking a basis in the Lie algebra, you define a map that is going to map into the dual of the Lie algebra, right? So when you are in this setup, you happen to have well, a Poisson structure here. You happen to have a Poisson structure here, as we saw in the previous talk, right? And well, if this is coming from a Lie algebra or from a group algebra action, well, you have such a structure here, and you also have this structure here, right? So, a natural question that we could ask is, when is this map going to preserve the Poisson structure? When is this going to be a Poisson map, right? Or when is this map, this momentum map, going to preserve this Lie algebra or group action that we started with? So we will see that these two questions, they are linked, right? And that's this general question that they wanted to address. And the key is equivariance. So equivariance is when this natural action that we have in the dual of the Lie algebra, you can flip it with a momentum map. So you have the action on the manifold, you have the action on the dual of the Lie algebra, and if you can flip them, then you say that your momentum map is equivariant. So when you only have a Lie algebra action, this is how this would look like, which is equivalent to this beautiful relation that you see here. So this is infinitesimal equivariance, and when this is coming from a group action, you would call it coadjoint equivariance. Okay? So right. So when do you have such a thing? Because first, in general, you have a momentum map. Can you choose it equivariant? There are situations where you can do it. So there is this proposition that James Montaldi proved in 1997, and which is that whenever you have whenever you have a compact group, basically by averaging, you can choose it to be equivariant. Okay. So anyway, you can also go to the semi-simple case when you are dealing with Lie algebras. But in general, you do not have this, right? So what is the situation in general? The situation in general is this construction by Souriau that I wanted to review with you for those who don't know it, which consists on constructing what is going to be called the non-equivariance one co-cycle. And it's a non-trivial construction, because you see what you do is you take the combination that measures the difference of the momentum map not being coadjoint equivariant. So if the momentum map would be equivariant for any C that I choose, right, actually this would be equal to 0, right? Because you can just flip this with the coadjoint action here. So, but notice that I'm defining this map that goes from G into G star, but actually I picked a C in order to define it. So under certain connectedness hypothesis, the first thing that Souriau proves is that actually this construction does not depend on the C that you choose. And the other thing is that it happens to be a G star valued one co-cycle, and we will see that this is very important. It satisfies the co-cycle identity using here the coadjoint action. So anyway, and actually this behaves very well with respect to the choices of momentum maps. So if you take another momentum map for the same canonical action of G on M, then actually you're going to get another co-cycle, and they happen to be in the same group cohomology classes. So the difference is going to be a one coboundary. Anyway, so this is Souriau's definition. So it turns out that, okay, in general, you are not going to have equivariance of the momentum map, but if you modify the coadjoint action in G star by this affine part that comes using this one co-cycle, then automatically by construction you are going to have equivariance. So in general, you do not have equivariance with respect to a coadjoint action. You have equivariance with respect to a affine action that you are going to construct with this Souriau's one co-cycle. So anyway, this is the construction that goes in the case in which you are in the presence of a group action. And what happens when you are in the Lie algebra situation? And then in this case, you basically follow the same program. So instead of defining a group co-cycle, so what you do is you go via this infinitesimal non-equivariance 2 co-cycle, And then you do exactly the same thing that we did before. So we take the difference that measures how non-infinitesimally equivariant the momentum map is, right? And then the same thing that used to happen before happens here. So basically this capital sigma does not depend on the choice of the pointer that you use to define it. And more importantly, you can prove that it satisfies the two co-cycle identity. So there is this Jacobi-like expression, which, as we will see, is extremely important for what follows. Because you see, up until now we are worrying about equivariance, but I promise you a relation between this and the momentum map being Poisson, right? So this is what I will be explaining to you in a second. And the fact that this holds is crucial for what I'm going to tell you to hold. So the same as before. So you see, before, just by using this modified affine action, you would obtain that the momentum map is going to be equivariant with respect to it. At the infinitesimal level, if you modify the Lie algebra action on G star, then by this element in here, you are going to recover exactly the same situation. So infinitesimally and from the group point of view, depending on what situation you are, both things work very well. And then now we are going to get into the Poisson part of the story. So you see, we know that if you take the dual of a Lie algebra, you have this God-given Lie Poisson structure that makes G star into a Poisson manifold, right? So let me consider this construction. So what I'm going to do now, instead of taking G, I'm going to consider this central extension of it using this two algebra cocycle that I introduced when we were talking about non-infinitesimally equivalent momentum maps. So anyway, with this, given the two cocycle property that I told you about, this thing that look like Jacobi, this makes, with this pairing, you can construct, you can endow it. So what you end up having here is a Lie algebra structure. You have a dual, and then the dual has a Lie Poisson structure, which happens to have this as a bracket. So it's the usual Lie Poisson structure, right? And then you have to correct it with this affine part that is coming from the capital sigma that we introduced before. So anyway, what is important about this is that actually, if you fix the A, so basically you are restricting to G star in this central extension, you happen to have a Poisson submanifold of this G star sigma, right? And basically, if you think of G star direct sum with A as just G star, what this is giving you is a new family of Poisson structures on the dual of the Lie algebra, which are these affine Lie Poisson structures that I am defining here, right? So the importance of this construction, which in general you have it here in full glory, right? And which, as any Poisson structure, they are going to have transverse Poisson structures of the type that we saw before. They happen to have symplectic leaves and so on. So for which I'm going to have symplectic forms that are going to be an affine generalized version of the constant Kirillov-Souriau symplectic forms. So the importance of that Poisson structure is that this is the Poisson structure on the dual of the Lie algebra with respect to which a non-equivariant momentum map is going to be a Poisson map. So this is the punchline that you need to have in your head. And that's why we constructed all this. So we started with a Poisson map in a very general situation which happens not to be in general equivariant. We made it equivariant. It was not, because we didn't have, basically this did not have these Poisson map properties, and by modifying the Poisson structure in the dual of the Lie algebra, we happened to make it a Poisson map as we used to have when we were considering coadjoint equivalent momentum maps. Anyway, so this thing that I just said, this is what you have in this statement. And this is what motivates, if you want, the construction that Richard in his paper worked out for the symplectic affine situation. So there are a few more facts that are well known. I will not get you bored with this. So if you are interested, well, you have it either in Souriau's book. This is in, well, you have it in Raju's book on mechanics and symmetry. You have it in my book with him on reduction of Poisson manifolds with symmetry. And anyway, so if you want, this is the affine generalization of the, I usually say Kosten, Kirillov, Souriau, but there are other names associated to it. So this is the well-known Poisson structure that you have for the symplectic leaves that happen to be also projections of certain coadjoint orbits of basically a Lie group that is going to integrate this central extension that I introduced before. So the entire theory that we teach basically first year graduate students generalizes to this more sophisticated situation where in principle we do not have equivariance or Poisson as a thesis or as a feature of the momentum map. Anyway, this is Richard's paper, so I will go very quickly over it because what he did is he took this general setup that I told you about and he worked it out very much in detail, so Cushman style, with all the computations in full glory for this specific case. So he took the affine real symplectic group, and so this is the group, right? And so you have here you have the Lie algebra 2, right? So here you have the bracket, right? So I'm just reproducing what you have in the paper. I will not go through all the details. You have them in the proceedings that we were given this morning. And right, so this is the action, right? What you have in this equation 4. And this is the momentum map. Oh, sorry, this is a momentum map. So if you just set up Hamilton's equations and you try to integrate it, the first thing that comes to mind is this. And sure enough, that's what makes it interesting and if you want pertinent in the context of the presentation that I made before. It happens to be non-equivalent. So actually you have a very nice expression for the infinitesimal non-equivariance co-cycle. So I just keep cranking the wheel, so I'm going to compute the central extension so that I know what the affine structure is going to be. That will make my Poisson, my momentum map a Poisson map and infinitesimally equivalent. So I just show to you what the expressions are. So this will be the central extension, this G with hat, right? And then again, the expression is very pretty, and is totally explicit. So this would be the result number 1. Result number 2 is the isomorphism to something that, to tell you the truth, I had never used before, which is this odd real symplectic group. So he proved in this section in the paper that there is this injective homomorphism. So, which is very natural again, and in any case, he has to choose bases, and the proof is somewhat convoluted. So these are things that are not that have some more content, and in any case, so there is this this map, and then you prove that what you obtain in the image is the so-called odd real symplectic group. So right. So anyway, so here you have the Lie algebra, you have the momentum map when it comes to the extension. And anyway, I just hope that I presented properly what Richard intended in this paper, and that you got some context for his work. And then I wanted to conclude with something that I will conclude tomorrow also in my keynote talk, is, with Manuel de Leon and Andrew Lewis, 15 years ago, we created a journal. The journal was the Journal of Geometric Mechanics. So this was published by Ames. We had this, we still have this really fancy editorial board. And actually, it was the late Jerry Marsden, one of the people who motivated the creation of that journal. In recent times, like 1 year ago, Ames changed their policies. So somehow they wanted more and more to make us into a predatory journal. They wanted us to publish like crazy, the usual predatory practices. So we just all resigned. So French style. We made a revolution, and in 6 months the whole thing was over. And then we refounded the journal with this name, which we like very much. Geometric Mechanics, exactly the same editorial board with some new young additions. So the journal is working up and running since basically 5 years ago, right, Emmanuel? So 5 years ago it's up and running. So we invite you to submit your papers here. We will handle them very well, especially because we need them. So next March, you see here in March 2024, we need to have a volume. So please help us, because you see, we made this gesture of, after 15 years of work, resigning and starting from scratch. But it's a lot of work, and we just hope that the community will help us to put it together again and to continue the glorious history of the previous journal. Okay, so thank you very much.
Thank you. I don't know if you want to answer a question, or because as it's not your.
If I can, but
we have one question.
Thank you very much for this nice talk. You have this new Poisson structure, which is, this is plus or minus bracket sigma. And I wanted to know on G star.
Right,
yeah, you have this, right. So take one of them. And I wanted to know if it is compatible with the...
you mean with respect to the original action?
Sure.
That's a good question. I would have to think it through. I cannot do it in my head, but that's a good question. I cannot do it in my head, but that's a good question. Anybody knows the answer? This should be super standard. No. No, it's not trivial.
I couldn't do either, my head.
No, it's not trivial.
Yeah.
In order for this to be as round, as nice as it is, it should be. But I cannot do it in my head. So, no, very good question. Thank you. Yeah, no, I will think about it.
Thank you very much, Malcolm.
Okay.
Thank you.
Thank you.